My name is Ariel Anbar. I'm a professor here in the School of Earth and Space Exploration and also in the Department of Chemistry and Biochemistry at Arizona State University. And I also oversee our astrobiology program here at ASU. Sarah says I'm world-renowned, which is pretty, in the email she sent around, which is kind of frightening, actually. Maybe it'll be notorious after this after this conference here. So my research, for those who don't know what I do, I focus in particular, about half of my group's research focuses on trying to understand the ancient Earth, evolution of the ancient Earth, in particular the change in oxygen in the Earth's atmosphere over time. For the first half of Earth history, roughly, there was very little oxygen in the atmosphere and environment, as far as we know. That's the conventional interpretation anyway. Most of us buy it. And somewhere around 2.4 billion years ago, there was a change, what we call the Great Oxidation Event, that led to, what that oxidation event was a large rise in oxygen. Large meaning a lot more than almost nothing, but still much less oxygen than we have today. And that transformed the world, though, about halfway through Earth history. We went on a one-way street from a planet that was dominantly anoxic to a planet that started to be oxidized and paved the way for life like ours, which views oxygen not as a toxic byproduct, but as an essential part of metabolism for which we get our energy. And so that was a singular event in Earth history. I've been fascinated by that since I was an undergraduate. It's what pulled me into geosciences in the first place. It ties to astrobiology in several ways, obviously, one of which is that is the possible use of oxygen, or ozone, which is a byproduct of oxygen, as a biosignature to look for evidence of life around on planets orbiting other stars. And so I've always been fascinated that this study of what happened in the Earth's distant past provides very useful information for trying to search for life elsewhere in the universe. It's not just academic interest in the ancient Earth. It ties to this very pressing question that drives many people, I assume most people in the SAGANet community, this interest in are we alone and what else might be out there and how might we actually figure that out. So that's my interest in a nutshell. Sarah, you let me know. I can go into a bit more detail into what I do, or I could take questions at this point. I don't know how you like to have these things flow. Any questions, or should I just ramble some more? I could talk about virtual education initiatives, sure. We'll get to that. Let me see, Sandroy. If the Earth was larger, would that have delayed oxidation, thus evolution of humans? Sandroy, so that's a great question. So one of the questions that we've started asking in our astrobiology team here, especially as we look to the next big astrobiology competition that you know all about, is this question of how would the rise of oxygen be affected by different planetary conditions. So not all stars, for example, have the same carbon to oxygen ratio as the Earth's, as our star, as our sun, which means that the planets orbiting those stars may well have different carbon to oxygen ratios. The more carbon to oxygen you have, the more reducing the planet's going to be, right? And so the less likely it is, or the harder it would be for biologically produced oxygen to lead to accumulation of oxygen. So that's just one example, right, of how variations in physical properties and chemical properties of planets could affect the ability of a planet to accumulate oxygen, even if you have biology producing it. So you're asking, Sanjoy, about the size of the planet. That's interesting. What does size do to plate tectonics, for example? And what would the consequences be for the rise of oxygen? I think the answer is we don't really know. What there are other questions popping up here, perhaps about your biochemistry work. All right, okay. Let me go back and answer or talk about the education stuff we're doing that Sarah brings up. This is a pretty digitally wired community here on Sagan, I imagine, so this might interest you guys. So one of the things that I've been putting a lot of effort into is finding ways to leverage all these new digital technologies for education. And the thesis of a lot of that work is that I think we can probably teach a lot of these topics and teach science in general much better than we do in large undergraduate courses in colleges right now, and that digital technologies can actually help us do that better. If you think about it, sitting in a lecture hall of 200 students is not a very enlightening experience for most students, even when you have a brilliant lecturer like Carl Sagan. Well, maybe Sagan's an exception. That may be an enlightening experience for all the students there. But typical lecturers, most of us are not at Carl's brilliance, and typical lecture class is not a very great place to learn science. We try to remedy that by having laboratories where you get more interactive, but the reality is that most large college science laboratories are not great experiences either, because for all sorts of logistical reasons they can't be all that exploratory. And so one of the thoughts we have is that online, using sort of borrowing philosophies from gaming, we ought to be able to teach science in a much more interactive way, where students interact with simulators, simulated environments, have to solve problems and puzzles, kind of like what you do in a video game, and learn in a much more engaged way. And so so that's something we've been putting a lot of effort into, using astrobiology actually as the theme. So I'm going to send you guys to a website here if you are interested in this sort of thing. If I can actually type. This is a website that is a teaser of what we're doing in our class. It's me and Lev Horodisky here at ASU, working with ASU Online and Smart Sparrow, which is a company in Australia that's very interested in what we're doing educationally, and makes software tools that allow us to build the kind of course we want to build. So this, I'll put a little slug here. This is a teaser for a online astrobiology themed course aimed at non-science majors, but not skimping. So we're very interested in using digital technologies for teaching this sort of stuff. And I'm going to send you to one other site here, and then I'm going to catch up here on this and probably see that nobody's interested in digital education. They want to learn about the Earth, but hold on a second. So one other technology that we're working with here are virtual field trips. This is a byproduct of our astrobiology program. It's one of our education and public outreach things here. And this actually ties into some of the science we just started talking about. The way geoscientists like me, my formal training is in geoscience and chemistry, the way geoscientists like me learn about the ancient Earth is you go and look at ancient rocks, right? And you try to figure out what you can tease out of the record of ancient rocks about ancient environments. And that necessitates a certain amount of field work and understanding at least something, even if you're lab-based. My research tends to be more lab-based. I'm the guy who takes the rock and tries to figure out what you can measure in a rock to figure out what the ancient environment was like. But people like me especially need to have some appreciation for the physical context from which those samples came, and the complications and confusion and that arise from geological context. We shouldn't just blindly trust our field geology partners to have gotten things right. We should have some understanding of what they're doing. But going into the field often, especially some of these locations, is not something you can do easily. And so we started thinking about, for that reason as well as educational reasons, we started thinking about creating really rich virtual field trips of important environments, important locations on the planet. And so we've started building these things. This was originally the brainchild of Carol Oliver at the Australian Centre for Astrobiology. She made the first of these virtual field trips more than about 10 years ago now. And what we've done is we've updated that concept using much more modern technologies than what Carol had access to 10 years ago. So if you go to that website, you can play around with these things. They're immersive spherical environments with gigapan images and videos laid inside the environment. And increasingly now we're also building interactive lessons within those environments that can guide students through. So it's not just, oh, here, look around, explore, but look, here are some questions you have to answer and things you've got to figure out by using the imagery and videos that we give you access to in this environment. So yeah, I think digital, to come back to Sarah's question, there's a lot of negative stigma associated with MOOCs. What are my thoughts on what works and what doesn't? Yeah, there's a lot of stigma, partly because academics are very conservative and don't like change, paradoxically, and partly because a lot of the MOOC experience is not very enlightened. There's been a rush to put a lot of what's a MOOC? Hold on, Sandra, we got to define this. Massively open online course. So a MOOC is a massively open online course. These are courses that enroll thousands or tens of thousands, or in some cases even hundreds of thousands of students online. They're typically free, hence open, and they're online. They've got a bad rap because they have poor completion rates. 100,000 students may enroll, but 1,000 students finish, which is not exactly not great. Yep, like Coursera, Sandro, exactly. The problem, so partly, we say a little cynically, academics are a very conservative bunch. We know what we're doing. We think we know what we're doing. We like to do it the way we do it, and we don't like change. That's part of the problem. But a bigger part of the problem is that a lot of the initial online courses that are out there are pretty lame. They are essentially videos of lecturers. So you take a lecture, which is already not a great teaching format, and then you videotape that and slap that online, so now you lose the spontaneity of a lecture because it's just watching somebody drone on for 40 minutes, and connected with some PowerPoint slides. Those of us who lecture know that lecturing from PowerPoint slides is already not a great way to lecture, so now you put that online. That's not that exciting. And then made it to typically multiple choice type questions to see if students are mastering stuff. It's taking the lecture format. Most MOOCs are taking the lecture format, which is not a format that is pedagogically all that great. The lecture format only exists, if you think about it, because in a pre-digital world, that's the most efficient way to teach a lot of students. So it's taking that model and then slapping it online, not doing anything really to take advantage, or very little to take advantage of the unique attributes of the online medium, right? So those of you who play video games know you can do stuff digitally that blows away what you can do in a lecture hall, and yet most online courses don't even try to go there. So we aren't doing much to take advantage of what's going on. So that's why that would be my comment on MOOCs. I think MOOCs have been really good at raising awareness that there's stuff to do online, but and getting hundreds of thousands of people interested in the concept. But we have a long way to go to actually take proper use of the online medium. So let's get back to science. Has there been significant fluctuation in dissolved oxygen levels since, before, after that 2.4 billion year period you mentioned? Yes, absolutely. So first question is, what was that transition? That transition was not to the modern oxygen level. That transition was from something like oxygen being a part per million in the atmosphere. So context, today oxygen is 20% of our atmosphere, so a part per million is almost nothing. So the first half of Earth history, we think oxygen was maybe around a part per million. And around 2.4 billion years ago, it goes up to being, maybe a fraction of a percent of today's level. So it becomes more oxidizing, but it's nothing you could have breathed. You could have survived in. It's not something you could have breathed in. So there was another step in oxygen, at least one more step in oxygen, we think, about 1.5 billion years later. So around 1 billion years ago, somewhere between 1 billion and half a billion years ago, it looks like there was another step increase in oxygen. And it's probably not a coincidence that that's associated with the first appearance of multicellular organisms on the planet. And so we think that oxygen has varied at least twice through time in a big way. Once at 2.4 billion years ago, and then again, somewhere between 1 and a half a billion years ago. And in between, there's probably a lot of variability that we just don't have the ability to detect. Our ability to detect changes in oxygen in the past is very, very crude. We're relying on very indirect measurements, very indirect signatures that we find in ancient rocks. And that's crude because the fingerprints of oxygen in ancient rocks are crude and imprecise, and the ancient rock record is crude itself. There's a lot of gaps. And so our ability to really detect variations in oxygen is quite poor. But almost certainly it was there. They were there. So that's pretty interesting. How does the history of O2 on Earth give us insights into the atmosphere of exoplanets? Is it really a good biosignature? Is it a good biosignature? Well, I've seen, there is at least one scenario I've seen where you can get a lot of oxygen in an atmosphere without having biology. I believe that, if you take a planet, put it around a red dwarf star, we have a higher UV flux. You can photolize water. You can break apart water molecules and generate oxygen that way. And if you're in the right conditions, you can generate a fair amount of oxygen in a planetary atmosphere without biology. But that's a very special circumstance. And so in general, certainly if you found a planet around a sun-like star, an Earth-like planet around a sun-like star, and you saw 10, 20, 30% oxygen in its atmosphere, we have no way to explain that right now, as far as I'm aware, without invoking biology. So I think it's hard to get a false positive for oxygen as a biosignature. The powerful question to ask, it's one of the questions we're asking in our astrobiology team now, is can you get a false negative? In other words, if a planet doesn't show oxygen, what does that tell you? And we know from Earth's past, we think there was a lag, most of us think there was a lag of a few 100 million years at least, between when oxygen production first started on Earth and when oxygen accumulated significantly in the atmosphere. And so right away from Earth's history, if we accept that interpretation of the geologic record on Earth, that tells you that you could have false negatives. You could have situations where biology is producing oxygen, biology is there, biology is producing oxygen, but it's not able to accumulate in the atmosphere. And so one of the things we'd really like to understand is what controls the accumulation in the atmosphere, and what are the limits to that, right? So if you tweaked the mass of a planet or the chemical composition of a planet a little bit within the realm of what we think is out there, can you get scenarios where you have vast volumes of oxygen production, really active biosphere, but it just can't accumulate in the atmosphere? It can't pick up enough because, let's say, the carbon-to-oxygen ratio is high enough that volcanic gases are reducing and react with the oxygen and keep it from building up. So the false negative problem for oxygen, I think, is probably going to turn out to be a really profound one. So that's so is it a good biosignature? Yes, but it's like any signature, it's going to have its limits. And with oxygen, I think it's the false negatives that we're going to have to focus on, to think hard about. What came first? Sanjoy keeps asking. Complex microorganisms or the second rise of O2, chicken and egg problem? Yeah, it is a bit of a chicken and egg problem. The conventional wisdom, I think, would be that the second rise of oxygen enables the rise of complex life. And by complex, it's really not complex microorganisms. When we say complex life, it's really talking about more about multicellular organisms. Multicellular organisms, if you're talking about simple multicellular organisms that don't have circulatory systems like we do, you've got to somehow distribute the oxygen around, right? I mean, we have blood vessels and all this, and this whole complicated circulatory system, in large part to get oxygen around into all our cells, right? To distribute it around the organism. So take a simpler multicellular organism that doesn't have a circulatory system. How does it get oxygen spread around on all its cells? And it's mostly through diffusion, right? And so you need to have a high enough oxygen abundance in the atmosphere for oxygen to be able to diffuse through those cells. And so the conventional interpretation, Sanjoy, is that you need to have a rise of oxygen. That second rise of oxygen has to happen in order for multicellular organisms to really start to take off, for the environment to be conducive to those kind of organisms. But it's a logic argument. There's not a whole lot of data to really help you sort that out. Is nitrogen isotope fractionation a good indicator for Titan's aging atmosphere profile? I'm not entirely sure what the question is asking. Nitrogen isotopes are very powerful in planetary science for looking at escape of nitrogen from an atmosphere. So, for example, the ratio of nitrogen isotopes in Mars's atmosphere is different from Earth's. Mars's atmosphere is enriched in the heavier nitrogen isotope, nitrogen-15, as compared to the Earth, and that's because Mars is too small to retain all its nitrogen, so it loses the nitrogen at the top. So the atmosphere gets heavier over time. The heavier isotope accumulates compared to the lighter one. So that nitrogen isotopes are used that way in planetary science. I'm not aware of that being done on Titan, although the Titan's small, so it should lose nitrogen, but on the other hand, it's also very cold because it's far away, so it's harder for gases to escape. So I don't know what the story for that is on Titan. A basic question for geologists: how is oxygen levels measured in ancient Earth? Because oxygen isotopes are short-lived, right? Well, so how do we get oxygen on the ancient Earth? That's an excellent question. One of the ways, the way that my group does it, what we work on a lot, is looking at the abundances in ancient rocks that were deposited in ancient oceans of chemical elements whose mobility in the environment is very sensitive to the amount of oxygen. So let's pick an example. So we work a lot on the element molybdenum. So molybdenum is middle of the periodic table. It's element number 42. Those of you who have read Douglas Adams' Hitchhiker's Guide to the Galaxy know that 42 is the answer to life, the universe, and everything. So, of course, we'd focus on molybdenum. So molybdenum is an interesting element for a geochemist because its chemistry is very sensitive to oxygen. If you have oxygen in the environment, molybdenum moves around a lot. It accumulates in seawater, it builds up in seawater because it's very happy in an oxygenated environment. Whereas if you take oxygen away, molybdenum is not very mobile and doesn't accumulate in seawater. So sedimentary rocks that accumulate in an ocean that has oxygen in it, those rocks should have a lot of molybdenum in them. Whereas sediments the same types of sediments that accumulate in an ocean that does not have a lot of oxygen in it should not have a lot of molybdenum in them. And so we can look at the molybdenum abundances in ancient rocks to try to get a handle on changes in oxygen. That's one of the ways we look at it. There are a whole bunch of other indicators like that, these indirect indicators. We call them proxies of oxygen, that basically are things we can measure in ancient rocks that tell us something about oxygen abundance because of the chemistry of those elements or those signatures in how that chemistry interacts with oxygen. But all these tools, chemists, are really crude. They tend to be kind of binary. They tend to be able to tell us there was oxygen or there wasn't. And actually getting at levels, how much oxygen is really hard, and we haven't really figured that out yet. Other questions? Do I think plate tectonics is a requirement for life? No, I don't think plate tectonics is a requirement for life. I think plate tectonics is a requirement for a biosphere like ours, but I don't see why you would need it to have biology at all. I suspect that if you don't have plate tectonics, your biosphere probably doesn't live as long, because the ability of plate tectonics to take chemical components that have reached a particular sort of thermodynamic state at the Earth's surface, and you subduct them and you heat them up and you decompose and you bring them back in a different energetic situation, so that then they can re-react. That I think probably allows plate tectonics to allows life to persist longer, and perhaps for evolution to get more sophisticated, to lead to more sophisticated, or sophisticated is the wrong word, to more complicated forms, perhaps. Is it a requirement for evolution? No, I don't see why you need plate tectonics for evolution, but I think that if you have plate tectonics, then probably evolution can last longer before you kind of run out of steam at the Earth's surface. Life needs disequilibrium, right? It needs to feed off of essentially disequilibrium chemistry. So anything that keeps things lively at the surface helps you. What would the Earth look like today if we didn't have the rise of O2? Would it still look like ancient Earth or something different? That's a good question. Well, it would look a lot more like ancient Earth than it does now. It's a question of what are the what you're really asking is, what are the features of the ancient Earth, what are the features of the modern Earth, and if we compare and contrast, is oxygen like the dominant difference between the modern Earth and the ancient Earth? Certainly from the perspective of aerobic multicellular organisms, it's the dominant difference. So a glib way to answer that is that if you beamed yourself to the ancient Earth, you couldn't really look at it because you'd die pretty quickly. And if you took oxygen out of the atmosphere, same thing. So, yeah, from the perspective of a dead multicellular organism, I guess the answer to your question is modern Earth would look pretty much like the ancient Earth if you didn't have oxygen around. Do you think the evolution of oxygen and photosynthesis was a relatively difficult or improbable event? That's an excellent question. We really do not know. That's there's a strong driving force. There's a strong incentive. Evolution, to the extent that you can talk about evolution in purposeful ways, there's a strong incentive, right, to evolve photosynthesis. You're sitting on the surface, near the surface of a planet. Let's say you have some primitive life that doesn't have that ability. It's sitting on the surface of the planet. It's trying to find ways to capture energy from the surroundings, right? That's what life has to do in order to metabolize. And there's all this free lunch coming from the sky, right? There's these photons raining down on you. So it seems to me there's a pretty good incentive to figure out how to do that. That's not the way evolution works, of course. But if you have molecules that form that, let's say biology is forming them for other reasons that turn out to be able to capture photons and turn them into something chemically useful, that would be an advantageous set of molecules to try to continue making, right? So I would think there'd be a pretty good selection pressure once life stumbles into some early sort of antenna molecules that can do something with photons that other than fall apart. That would then drive you pretty quickly towards photosynthesis. So that would be my gut reaction, Dan. Oh, it's Dan Mills. Yeah, how you doing, Dan? Nice to hear from you. I didn't recognize the little picture. What do you think, Dan? You're studying this stuff, kind of. Cyanobacteria work by photosynthesis, and fossils were found as early as 2.8 billion years. Well, so the question is, the question suggests that photosynthesis takes off really quickly. I wouldn't be so quick about that. So the earliest really strong evidence of biology is about 3.5 billion years ago. So that's, and the oldest strong evidence of oxygen is probably around well, we argue about it. It's probably like 2.5 billion years ago. So there's almost a billion years between the strong evidence of life and strong evidence of oxygen. Now, if you push earlier, there is weak evidence of life going all the way back to 3.8 or weaker. There's also some arguments that there was oxygen around even that far back. That's not widely accepted. But the conventional view would be that you've got at least a billion years between having widespread biology at the Earth's surface and having a lot of oxygen at the Earth's surface. When photosynthesis began is a good question, but there could well be a pretty big lag. So I don't know that you can infer from the timing that photosynthesis took off quickly. I'm not convinced by Moyes'. Well, I think Sandra asks, you're not convinced by Moyes' 3.8 Achillea evidence. So I actually am convinced that it's evidence. And all that paper ever really claimed was that it was evidence, and I think that's fine as far as it goes. How strong is that evidence? It's worth talking about kind of evidence. It's not conclusive evidence. It's an interesting argument, somewhere between 1 and 2 sigma for those who think in terms of confidence intervals. How's that, Sanjoy? Dan, it's too ambiguous. What's too ambiguous, Dan? Do I think we'll find life in the solar system or on an exoplanet first? I don't know, Sarah. That's really a matter of opinion, huh? That's I go back and forth. If you asked me that a year ago, I think I would have said that origin of life is probably really hard, and we probably won't find another example in our solar system. But now I'm involved in this development of this mission idea to bring samples back from the plume of Enceladus, to do a sample return where you fly through the plume and bring stuff back, and that's motivated by the possibility that there could be biology, right, hypothetically, on Enceladus. And so, probably because of my interest in that mission, my bias has swung the other way. And so now I'm thinking, well, it's quite plausible that life, gets started wherever conditions are good enough, and maybe that's a pretty wide range of conditions. So I don't know. It's such a matter of opinion. It's hard to answer. What is the perk of being an astrobiologist? Why choose it as a career? Well, part of it is the perk of being an academic if you can get far enough in the career, which is you have an awful lot of intellectual freedom. Certainly once you're a tenured professor, you can pretty much take your work in any direction that's reasonable. That's pretty fun. Astrobiology in particular, you're making science fiction come true. When I was a grad student 20-some years ago, the idea that there could be planets around other stars was a hypothetical. And then towards the end of when I was a grad student, we started finding planets around other stars, and now it's boring almost, right? There's lots of planets around other stars, and now the really interesting thing is to start characterizing them. What are they like? What could be there? That's just really cool to be in a field that is advancing from imagination to reality at the pace that this field is advancing. And when you realize that this is a field where, hypothetically tomorrow, Curiosity rover could discover something that totally upends the way we view things. Certainly within our lifetimes, assuming we keep pursuing this stuff, within the next 10 years, we may well have astronomical data that upends our view of whether or not there's life out there. That's just really exciting. It's one of the more exciting fields to be in from that standpoint. So I think that's a big perk. And I'd say one other thing before leaving Sandra's question, the other big perk about being an astrobiologist is if you like science that combines different disciplines, if you like being in a field of science where you have no choice but to swing between astronomy and biology and geology and various fields, and if that gets you excited, then it's a great discipline, and that's a huge perk. Some people don't like that. Some scientists don't like that. They want to just focus on their thing. And for scientists like that, I suppose it's not a perk, but it's a liability. But for me, I find it a huge kick to be able to be in a field where being a generalist and being broad is an asset. Can I elaborate a bit about the biochemistry work that I do? So I don't really do biochemistry all that much. I dabble in some biochemical ideas. I'm very intrigued because my focus, as you may have picked up, has to do with, I mentioned molybdenum before, a lot of my research has to do with looking at metals in ancient rocks, metals whose abundances are affected by oxygen. Because of that, I've gotten interested in metals, the use of metals in biology, and what's the antiquity of that, and how are the choices of metals in biology affected by the abundances of metals in ancient oceans, which in turn are affected by oxygen. So there's kind of all this coupling and linkage. So to take molybdenum again, for example, to tie this to nitrogen that was mentioned before. So nitrogen likes to be the N2 molecule in the atmosphere, and it's very happy as the N2 molecule. It's a very strong bond, that N2 bond. But you need nitrogen in your body. Every organism needs nitrogen in amino acids and nucleic acids, other molecules. And so to make nitrogen biologically available, life has to actually put in a lot of energy, literally, to break the N2 bond and make that nitrogen biologically available. So there's a sophisticated architecture that has evolved to do that, an enzyme called the nitrogenase enzyme. And the most common form of the nitrogenase enzyme uses molybdenum in its active site. Take away the molybdenum and that enzyme doesn't work as well. So that kind of begs the question, did that and that use of that metal and that enzyme, did that evolve as a consequence of the rise of oxygen that led to more molybdenum being in the oceans, or was that metabolism hampered before there was a lot of oxygen and hence a lot of molybdenum in the environment? So I'm interested in those kind of biochemical questions. We don't really do that biochemistry here in my lab, but for the most part, but I'm intrigued by it and have written about it and like to talk to people who actually do it. So right, to talk a bit more for folks here. And I'm also interested in metal use in biology in general. So there's a student working with me, Mark Naveau, who's been on here, some of you may know. So Mark is looking at the elements that make up extremophiles at Yellowstone National Park and other environments. Because we want to know fundamentally what are the rules that govern, that dictate the use of elements in organisms. So I'm interested in biochemistry from that standpoint. And then I have a totally different biochemical side, which is not really astrobiological, but I'll mention it because it is NASA funded. So it's kind of astrobiology. And that's using, much of what we do in my lab involves measuring isotopes of elements. We can get yet more information out of ancient rock by looking at isotope abundances, isotope ratios, which get changed by various interesting environmental variables like oxygen abundance. But it turns out that there are applications of isotope technology in biomedicine. and in particular, it turns out that calcium isotopes in blood and in urine change, their ratios of those isotopes change when you are forming or losing bone. It's a measure, it's a biosignature of, different type of biosignature, the signature of your bone metabolism. The isotope measurements in blood or urine can be used to trace whether you're making or losing bone. So NASA is interested in that because when astronauts fly in space, they lose bone mass, and NASA would love to come up with better ways to monitor that, to be able to tell whether astronauts are gaining or losing bone. And so they've funded us to develop this technology, and it really does work. And we're now talking to biomedical researchers and clinicians, actually, who deal with diseases that affect bone metabolism, to see if we can make use of those calcium isotope measurements in patients and at a clinical level to help with disease diagnosis and management. So that's a whole other side of what I do that's kind of biochemical. More about Enceladus, what biochemistry you're most interested in. So yeah, Enceladus, in case somebody doesn't know, so Enceladus is this tiny moon of Saturn. That one of the big discoveries of the Cassini mission, which is at Saturn, which has been there for a decade now, one of the big discoveries was it found that this little moon of Saturn is spewing water into space. It has jets, plumes of water, geysers, essentially, that almost certainly stem from a subsurface ocean beneath. So it's kind of like Europa, and that you've got a moon that has a subsurface ocean, but unlike Europa, well, now maybe Europe has joined some recent discoveries, but until a month ago, we thought Enceladus was unique in having jets of water coming out of it. We now know there's a report now of plumes also on Europa, so Europa may also have the same kind of thing going on. So this mission idea is to take a spacecraft, send it to Saturn, fly it through these jets of water, and return to the Earth, and then analyze the material once it's brought back. That may sound crazy. It is a little crazy, but it's actually very doable. Our big challenge is to figure out how to do it within the budget that NASA actually has for different types for the lowest cost planetary mission that they have, what's called discovery missions. And we're close to getting it there. So this mission is called Life Investigations for Enceladus. The acronym is LIFE, kind of cute. We're developing it as a partnership. We're trying to develop it as a partnership with the Japanese Space Agency. They would contribute some of the hardware, which makes it more cost affordable. Plus, it turns out the Japanese Space Agency has great experience with sample return and great interest in doing sample return technologies. So it's a really nice intellectual partnership. And so we're trying to get this mission conceptualized well enough to convince NASA to invest in it, so that maybe in 30 years or so we'll have samples from Enceladus on Earth. And so what we'd be looking at the main focus of the mission is organic molecules. We know the Enceladus is interesting not just because it has water and spewing into space, but we know that water has reduced nitrogen compounds in it. So it's got biologically available nitrogen, and it has organic molecules. All that's been detected from the Cassini spacecraft. And so the next logical step, since we know there's organics there, which is, it's more than we know for Mars, actually. We argue about organics on Mars. We're pretty confident there's organics in Enceladus. What are those molecules? Could we bring them back? Could we look for chirality in them? Could we look for isotope abundances? Could we look for structural distributions? There are a whole bunch of things we could do if we had samples here to try to look for fingerprints of biology, or at least really interesting prebiotic chemistry. So that's the focus, is organic molecules that we would bring back from Enceladus. Emma, in our Devonian rise paper, we have lag between the increase of oxygen and the actual first fossils of lignin. So I don't know that paper all that well. There is, I apologize, Emma. I know I should know that paper. But I think, I feel a little uncomfortable digging into it too much, but I don't know what drove that rise. I like the idea that formation, just to fill other people in, so lignin and cellulose, what does that have to do with oxygen? Well, I'm a co-author on the paper, Emma, I know. I should have my head in it, but it's been a while. So lignin and cellulose. Why does that? What has to do with oxygen? So to accumulate oxygen in the atmosphere, you have photosynthesis that makes oxygen, and it also makes organic carbon. And if you re-react that oxygen to organic carbon, which is what all of us do to get energy, right? Then you chew up all the oxygen, and there's no accumulation of oxygen. So to accumulate oxygen, you not only need to have photosynthesis produce it, but you need to take the organic carbon that's also produced, and you need to somehow bury it. You need to take it away from exposure to the atmosphere so that you have some oxygen left over that can stick around in the atmosphere. Otherwise, it just goes away and you don't accumulate anything. So cellulose and lignin are interesting because they're kind of unreactive. They react much more slowly than other things, than other organic molecules. And so when you start making those kind of molecules, you're better able to sequester carbon, and that could lead to a rise of oxygen. So I think there's probably something. I buy that. My gut feeling, Emma, would be that lignin, cellulose, plant material, the rise of that, the origin of that, putting that on land, has got to make a difference to oxygen. It makes sense. But I don't know what the lag. The lag could just be the record is not great, right? I always worry about lags, leads and lags, and being mechanistic about them when we know that the geologic record doesn't preserve things all that well. So, all right, Emma, I hope I dug myself out of the hole there. Given more time, a question: is there evidence that the rise in oxygen coincides with reduction in atmospheric nitrogen levels? No. Well, so first of all, it's very hard to measure ancient nitrogen levels. Nitrogen is, as N2, is a very unreactive gas, so it doesn't leave fingerprints, right? It's kind of to leave fingerprints in the record, you need to react with stuff, and nitrogen doesn't react very much. So that's answer number one. And answer number two is that there's so much nitrogen in the atmosphere that even when you change the rate of biological nitrogen fixation because you have molybdenum around, you're not going to make a big difference in the nitrogen abundance in the atmosphere. So even if we did have ways of measuring paleo nitrogen in the atmosphere that were good, they would have to be extraordinarily sensitive, I think, to pick up any dent in nitrogen due to a change in biological nitrogen fixation. So qualitatively, Kamesh, that's an interesting question. Quantitatively, I don't think there's much of a story there. All right. I'm getting a sore throat now. And I gotta spend another hour talking now at my next event. So I'm happy to take another question. I've got some time. This is fun. Any last thoughts for me? There are so many thoughts. Advice for future astrobiologists. Gosh. Well, let me. Well, I don't know about advice. I think one of the main pieces of advice I would give young astrobiologists is don't listen too much to what older astrobiologists say about what you should be doing or how to do it, because it's such a young field that your knowledge becomes dated pretty quickly, and the field is evolving so rapidly as a discipline that the way that I got into the field is going to be very different from the way, and succeed is going to be very different from the way any graduate student today is going to get in there and succeed. So you got to be a little careful. Put a little asterisk next to any advice that any of us world-renowned astrobiologists might give you. That would probably be my parting advice. But let me give one other parting thought that's a little different. So one of the things I've become very interested in recently is the connections between astrobiology and our future here on Earth. And I don't mean by that we're going to meet space aliens who will give us new medicines or something like that. But I think the perspective that we bring as astrobiologists to thinking about life in a planetary context is a perspective that is going to be increasingly important in a very practical way to us here on Earth as we move into what we call the Anthropocene, this era where that's going to be defined by human civilization on a global scale affecting the planet. We are moving into a realm where we have to just deal with that reality that we're here and we have an impact whether we like it or not. And we have to think about how we're going to manage that impact and how we're going to be stewards of this planet. And that requires a planetary perspective on the relationship between life and the non-biological Earth, and the relationship between intelligent life and the rest of the planet. And I think that's a perspective that we as astrobiologists kind of have innately, and it's not a perspective that most people in the environmental community have innately. There is this tendency, when we talk about our neighborhoods or our cities or states or regions, we accept everybody, just about accepts the idea that we're here, we have an impact, we're not going away, we have to manage it somehow, we have to be very active in how we deal with it. But when it comes to the planetary scale, if in the environmental side of things, we tend to have this ethic that somehow the natural Earth is this pristine thing, and we're mucking it up, and the solution is to somehow reduce our impact ideally to nothing. And that's a very nice idea, but it's not going to happen, because that's just not the way life works unless we go extinct, right? And so we need to get our minds into a mindset of thinking about the planet the way we think about our neighborhoods, that we're here, we have certain values, we also have certain needs, and we need to find a way to balance all these things, and we need to manage the situation. And I think astrobiology forces you into that sort of pragmatic perspective on how a planet works as a planet and how life interacts with it in a way that the rest of the scientific community actually really needs. So there are going to be some interesting convergences here, and I urge you guys, if you have time, look for a talk, actually the Sagan lecture that David Grinspoon gave at AGU at the American Geophysical Union meeting last month. David has a very nice perspective on this, the synthesis between astrobiology and sustainability. I would go check out that video. It's definitely worth a look if you're interested in thinking about the practical, real-world connections that are probably coming between astrobiology frames of thought and our sustainability challenges. Here, I'm going to try to find the lecture link here for you guys. David's a really good speaker. Here we go. Here it is.
Good morning, everyone.
Wait. We just want the link. Here we go. Sagan lecture by David Grinspoon. The talk is titled, by the way, Terra Sapiens. Right, the emergence of a planetary intelligence. If we're going to survive on this planet or thrive on this planet, we need to evolve into being in a planetary scale intelligence, dealing with a planet in an intelligent way, and that's an astrobiology kind of concept. And now I'll stop rambling. So anything else? Shall we wrap up? I need to get over to another building in 10 minutes, so this is probably a good place to end. Thank you. It was fun. All right. Well, thank you all. It's been entertaining, and be glad to answer any further questions. Feel free to email me, and look forward to seeing you some other time.